So let's get started.
Sure. And please don't forget to record who you already did. So.
I think it is. It's recording at the moment. So, okay. So hi, everyone. Welcome to our virtual Lunch and Learn for December. It's great to see so many of you join us here today, and we do hope you enjoyed this month's topic, Getting Machine Learning Models into Production. My name is Mark Foa, and I'm a Client Engagement Principal and Machine Learning Practice Lead here at DiUS. After a quick introduction about DiUS, you'll be hearing from Shahin Namin, one of our machine learning specialists. He'll start with a brief overview of machine learning. He'll then talk about why getting machine learning models into production can be difficult, and then share some insights and tips to help you along with your own journey. Following the talk, there will be time to answer any questions you might have. We'll use Slido again to capture those questions, so please go to slido.com and use event code 37432. We'll also put the link in the chat window as well. You can submit your questions during the presentation if you'd like. They'll be shared and addressed at the end of the talk. Again, we have quite a diverse audience today, so we'd expect the level of technical understanding of machine learning to vary. While Shahin will highlight some of the organisational, cultural and people challenges, this talk will mainly focus on those technical aspects. And of course, in addition to tech, we all know there are other concerns that typically need to be validated as well, such as product desirability and viability to ensure success and return on investment. But that's a topic for another day. If you have any questions that might not be addressed during today's talk and Q&A, or you'd like to dive even deeper into the technical details, we'd be more than happy to connect with you after today's session. Now, before I hand over to Shahin, a quick introduction to DiUS for those who don't know us already. We're an Australian consulting company. We're all technologists at heart, and as the title suggests, we like to start with customer problems first and use technology, including emerging technologies and practices, to best solve them. We love building end-to-end solutions for those, for and alongside our clients, and we also build our own products. So many of the lessons you'll hear about today are those that we have learned along our own product journeys. DiUS is quite unique in that we have deep in-house expertise across digital data and devices and how to bring it all together, from experimentation right through to the rigor required for production. And we do all of this with a cross-functional approach and experience design at the heart of it all. Over the 16 years since we've started, we've worked across most, if not all, industries and have solved many interesting and complex problems that have not only required our digital and cloud expertise, but also IoT and machine learning. Today's talk, however, is focused on machine learning, which, as many of you already know, is quite a broad and growing space. At DiUS, we've worked across a number of application areas, including computer vision, which many of you would have heard during last month's Lunch and Learn, NLP, conversational AI, anomaly detection, and recommendation systems, to name a few. Now, without much further ado, over to you, Shahin.
Thanks, Mark. Hi, everyone. I am Shahin Namin, and we will be talking about productionization of machine learning models in this talk. I will kick off with an introduction to machine learning here. Presentation mode. So in machine learning, we aim to train models that try to learn from the data. We expect the models to be generalizable, which means that after the training is done, we expect the model to be able to provide prediction and guess the output for a data sample that it hasn't seen before. Machine learning can be used for addressing different problems of AI, computer vision as an example, which is machine learning on images and videos for the sake of recognizing objects and detecting objects in images and tracking them on videos. It can be used for recommendation systems to provide personalized recommendation to users. It can be used for prediction as an example, time series prediction, which can be sales or market trends and other applications. Natural language processing is another big area of machine learning, where the machine learning model tries to learn from text and learn the languages, and it can be used for applications such as translation, text summarization, sentiment analysis, and other applications. So there are other applications of machine learning as well, but we think that machine learning is useful for helping with decision making. It can be used for automation and control. As an example, it is heavily used for autonomous cars. Advertising and marketing and trying to promote content can be addressed by machine learning. And these are just to name a few. There are obviously a lot more applications that can be handled by machine learning. So for a machine learning project, we need to train models, which means we try to prepare models, mathematical models, in such a way that we introduce a set of data that we call training data set to the model, and we expect the model to learn from that data. In practice, we usually deal with supervised learning, which means our training data is fully labeled, and we know the desired output for every single element in the training data set. So labels are very expensive when it comes to different applications, but they are a valuable asset, and it is worthwhile investing in labeling the data for different applications. And having good labels will result in better and more accurate models. When it comes to learning and training machine learning solutions, there are different spectrum of options that we can choose from. Machine learning as a service are the services that are provided by cloud providers, and they don't need training. They are off-the-shelf API tools that can be used very easily, but they are generic and they might not be suitable for some applications. But different applications can be addressed by them, such as OCR and some computer vision applications. The next option is AutoML, which is another option that we can choose. For AutoML, we introduce our training data set to the AutoML component, and it goes and trains a model without having human intervention. And you can download and use the artifacts of that model. So you don't get involved in implementing the model, but you need your training data to use AutoML. As we move toward the right of this spectrum, we take charge in implementing custom models, and we can use state-of-the-art models at the right of this spectrum. Obviously, we get more flexibility, and the model can be more flexible and specific to our application. And we expect to get better performance because we can use state-of-the-art models there. But the trade-off is that there are more complexities that are added, and there are more challenges when it comes to productionization when you move towards the right of the spectrum. So this talk addresses mostly productionizing the state-of-the-art and custom models and the challenges that we face there. So we usually start from the data in organizations. The first step is to implement data pipelines and make sure that we can import and stream the data into our system. The next step is to prepare the data lake, which is a repository that tries to keep and store all the available data in such a way that we can interact with the data. After that, we recommend running a machine learning proof of concept. The proof of concept aims to reduce the risk of the project and make sure that the data is ready, and it gives us confidence that we can learn a model on top of the available data. And the last step is to productionize and make sure we can provide useful services for the end users. As we move from the left to the right, in the beginning, data engineers are more active and they are in charge of writing the data pipelines. Machine learning proof of concept is usually done by machine learning engineers. For productionization, we need machine learning engineers and data engineers to work hand in hand. And we need a lot of collaboration for that to be successful. Another point to make is that data lake preparation is a heavily involved step. Sometimes we try to postpone that and we try to prepare the data lake along with the productionization of the machine learning model, because we don't want to stop the project in the data lake step, which might be a huge step. And also the highest impact is when you productionize your machine learning models. So this talk mostly talks about the right-hand side of this journey. And this is the least spoken part in this journey. You can find lots of talks that talk about experimentation and machine learning proof of concept or data lake preparation and so on and so forth. So we are addressing the right-hand side of this spectrum with this talk. With machine learning proof of concept, what we do is we try to prepare models and train the models and make sure that we can have highly performant and accurate models on our data sets. So the steps to take is to prepare the data, to analyze and do feature engineering. Features are the values that you pass to your model, and they should be good representative of your data. And the aim of proof of concept is to make sure we can train models on top of the available data and that the concept can work. We run proof of concepts to make sure we reduce the uncertainty and risk of the project, because we want our machine learning models to be performant in practice, and we just want to make sure that we reduce the risk of having a model in the end that is not as accurate. But the outcome of proof of concept is not a production-ready system. It is a set of artifacts that we might use for production later, but also it is not a production-ready system. It is just to reduce the uncertainty and risk of the project. So when it comes to productionization, we know that it is hard, and we're going to look and see why machine learning projects might fail. So more than 85% of machine learning projects don't make into production. One of the reasons is that sometimes there are not clear goals and reasonable expectations for machine learning projects. And therefore, we try to upskill our clients and try to make sure that their expectations are reasonable, and that way we can define clear goals and aim towards that in machine learning projects. Data and labels are another blocker sometimes, because if the quality of the data is not high, or if the data is not ready, we might not be able to train performant models, and that's why we run proof of concept. As I mentioned, during the proof of concept, machine learning engineers try to focus on models and improvement of the models that they train. So it's a narrow focus, but when it comes to practice and productionization, there are many more concerns that need to be addressed. And therefore, we need to involve other specialists in our team and use them for productionization. The other complexities that we face in productionizations, some of them come from the data and the model. We have to make decision on whether we want to do all the computation on the cloud or on the edge. We had another talk that we talked about a use case in insurance, phone insurance, that we showed some models that we used on the mobile devices, but IoT and other devices might be used for edge processing. There are considerations there. Sometimes you need to convert your model by techniques like quantization, or because your IoT device might not be computationally strong, you might need to shrink your model and make sure that your device can handle the amount of load. And therefore, techniques like knowledge distillation come useful. Model size has inverse proportion to latency. So as we increase the model size, we get improvement in the model performance, but we need more computation, and therefore the latency will increase. We need to retrain our models in practice, and this happens in almost all different projects. And because we need to retrain and prepare more models, we need to deploy our models into production frequently, and therefore we need to invest in techniques that we can deploy our models along with other parts of the system quickly. There is no guarantee that our newly trained model works better than the other models, so we have to make sure we keep versions of the data and the model, and we can roll back to those versions if our mostly recent model doesn't work well in practice. Also, machine learning models can process the data in batch mode or in real time. And depending on the application, we might use one or the other, and the infrastructure is different when it comes to these two different pipelines. As an example, in recommendation systems, you might need to send requests to your model and get responses quickly as someone is interacting with your website to provide some personalized feedback according to how they are browsing the website. But also, you might have an offline and batch processing system that goes and tries to update the model. And next time the user goes back to the website, the first page might show the user personalized items. Therefore, we might need to use batch processing as well as real-time data in some specific applications, or choose one or the other. When it comes to the infrastructure, there are complexities that arise in machine learning projects. So we need to use GPUs and TPUs in machine learning projects, and therefore the cost of the infrastructure will increase dramatically and very quickly. One way to address this problem is to have implementations that are serverless and to try to use serverless components. And that way we can exploit the pay-as-you-go pricing in the cloud, and therefore we incur lower costs for the infrastructure. High availability might be an issue for some projects, and that means we want to have replicas of different components, as an example, the model in different availability zones, and depending on the amount of load, we might route them to different availability zones. Resiliency is important for some applications, and usually our enterprise clients can't afford to have downtime. Therefore, we have to make sure that our system is resilient, and in case there is a failure in the system, we can shift to another region and fail over to another region without any downtime. Depending on the amount of load, we might use auto-scaling tools so that we have high throughput. And with auto-scaling, we need to have health checkers so that we can make sure that our system is up and running, and we are able to respond to the requests in timely manner. So this helps with the cost optimization as well, because we can scale in and out the components and the infrastructure based on the amount of and the volume of the requests that we are processing. Logging and monitoring is also very important because we always have to make sure that our model is accurate and is working properly. So we have to do monitoring and logging of the model as well as the other components like the infrastructure in machine learning projects. And it's even more vital and important to have logging and monitoring in machine learning projects compared to the other projects. There are a few non-technical challenges that arise in machine learning models. So organizational structures might impact the model. And there are cases where the data science team and the team that are in charge of productionization work in silos, and this results in failure very easily. We have to make sure that we have a team that is dynamic and cross-functional, and everyone interacts and collaborates with each other in machine learning projects. So there are a few recipes that we want to talk about that might hopefully lead to success for machine learning projects. This is how we try to tackle a machine learning project with time. So we first make sure that we work on the idea and we have clear and vivid goals for our machine learning project, and we have reasonable expectations of the machine learning models. Next, we move to proof of concept, and we purely focus on implementing highly performant models without considering any other constraints that we need to address in practice. After that, the next step is to concentrate on architecture and make sure that we have more data pipelining and ETL transformation pipelines in place so that we can have an end-to-end testing of the model, and we can test our model in practice and see how it behaves. And therefore, we invest in a very simple UI so that the users can interact with the model and we see the behavior of the model with real data. The next step is to try to implement more features and improve the models as time goes by. So after the proof of concept, we try to focus on the architecture. There are usually a lot of spikes in this step. We try to address pain points and bottlenecks first so that we can reduce the risk and we can make decisions on the architectural designs and infrastructure. Also, we invest in data pipelining to make sure that we have the stream of data coming and interacting with the model so that we can do end-to-end testing of our model, because in practice there are examples of failure for machine learning projects when our model works well when we train the model and on our test data. But in practice, we see that the data that the model is interacting with is different, and therefore our model is not performant enough. And we try to find if this is the case for our problem as soon as possible and try to address that as quickly as possible. For this step, because the focus is on the architecture, we might use a simple baseline or a machine learning as a service and just focus on the rest of the pipeline. Sometimes the artifacts that we have provided in proof of concept are also a good starting point, and we can start working and implementing them in production. So we always try to make sure we encapsulate the machine learning component, and therefore we use containerization. This helps with microservice architecture, and the reason is that we try to make sure we can change the model without impacting the rest of the system. And therefore, containerization is a very good fit here. And also, using containers, we can standardize the machine learning component and the API requests and responses so that later when we retrain the model, we can replace the container without impacting the rest of the system. There's another reason for containerization, and that is to make sure that our code is reproducible, because containers allow us to train our models without worrying about the infrastructure, and it guarantees that we get the same results if we use containers and fix the random seeds in practice. So in further iterations and steps, we try to make sure we invest in automating the training of the model, because this needs to happen in practice. Also, we have to make sure that we keep track of all different models and experimentations that we performed on the training data, because we might need to go back and use them in practice. Logging and monitoring is important, so we have to make sure that we gradually implement such components in our system. We invest in user interface and user experience design, so that we have seamless experience for the end users of our system. We gradually try to add more features and integrate our system with the available systems in further iterations. CI/CD pipelines for machine learning is another investment that we have to make and sometimes prioritize. And this allows us to do model retraining and even monitoring in a simpler way. Also, in different iterations, we aim to improve the performance of the model. When it comes to model performance, we have a set of recipes that we follow. This also applies to proof of concept as well. So we always start with defining a set of metrics, which are a set of numbers and scalars that give some notion of the model performance. We usually use more than one metric, because a single number usually is not a good representative of the model performance. So we have to take into account more than one number here. After we fix the metrics, we go and try to implement a baseline as quickly as possible. And for this, we can use simple statistical models, machine learning as a service, or AutoML, because these approaches allow us to experiment with the data as quickly as possible. But we don't expect to get our best results in our baseline. We just have a solid ground to compare our results with. After that, we try to iterate and improve our models within the constraints that are enforced because of the project, which might be the model size, it might be other considerations that we might take into account. But within those constraints, we try to make sure that we prepare our data. We try to extract the features from our clean data. And with clean data, we might need to remove the missing values, the records with missing values, or try to find a way to fill those values, and also work on the cleansing of the data and the quality of the data. After feature engineering, we try to implement and train our models and evaluate. And after evaluation, we try to gain insight by looking at the predictions of the model and also how the model is behaving in practice. And also we look into the model itself and try to gain insight. And based on that, we go and try to make decisions on what we are going to try next to improve our model in the next iteration. So there are many different techniques that are used here, and there are many different things that we can try. Depending on the situation, we might go and ask for better labeling or more data to be collected. So we try to enrich the model. We might use techniques like data augmentation in order to get better results. In our previous talk, we also talked about data augmentation on images. So please refer to our previous talk for that. We talked about data augmentation on images, and the good point about data augmentation is that we can make our models less variant to different aspects of the model. Like if it is images, it can be rotation or scale of the model. And therefore, we expect to get better results by using data augmentation. Also, we might work on feature engineering and make sure that we have better features in place. We might focus on a single model and try to find the right hyper-tuning parameters, which can be tweaked manually or automatically. We might also go and try to optimize the architecture of our models using techniques like architectural search. Also, we might need to move from the model that we have been working on and use state-of-the-art models and replace the previous models to see what we are getting by changing those models. So after each iteration, we try to look more deeply into the data and the model. So there are a few things to be mindful of. Bias and fairness is an important issue, and sometimes it occurs because there is imbalance in the data. And there are techniques that we can use, like sampling or SMOT, that we can use to tackle this problem, or we might go and try to collect more data for infrequent classes. Bias in labels is reflected into the model itself. So we have to make sure that there is no bias in labels, or if it exists, we have to go and try to relabel and remove the biases. Passing fields and features like race and gender to the model might make the model unfair, and therefore we have to make sure that we tackle this and remove these as input to the models. And sometimes we have features that are correlated with such features, and we have to try to find such features and remove them from the input. Also, we look at the predictions and try to find why the model is not giving correct predictions. So one reason might be overfitting, and that means we get good results on the training data, but our model is not accurate enough on the test data. And there are techniques for this, such as using regularization or trying to shrink the model. Underfitting is another problem where our model is not capable enough to learn from the data, and we might use larger models for such tasks. If we have incorrect labels, these incorrect labels are reflected into the data, into the model itself as well. So we have to make sure that we go and try to have cleaner labels. Uninformative features are important because if we have more features that we train our models on, we need to have more data, and the data grows exponentially by the number of features, and this is called curse of dimensionality. So we try to find uninformative features and try to remove them, and that way we expect to get better results with less amounts of data. Also, model interpretation is important. If we are using techniques that have attention strategies in them, we can look at the attention in the models and try to find where the model pays attention to and focuses on when it comes to predictions. An example is that people have done research and they realized that most of the models try to classify an image of a sheep by looking at the grass and the surrounding around that rather than the sheep. And such problems can be found by looking at the attention in the model. If the model is not interpretable, we can use techniques like SHAP and LIME. And by looking at them, we can find how the model behaves when the features and the inputs of the model change, and therefore we can gain insight on how our model is behaving. And by looking more deeply into the data and the model, we might choose what to do next and how to improve our model in the next iteration. Another problem is model degradation or drift. So machine learning models have an expiry date, and they expire and they degrade in terms of their performance. And this might happen because there is a change in the data, or the pipeline has changed and what the model is looking at is different from what it has been trained from. So in order to tackle model degradation, we try to retrain our model on the newly collected data. And in some specific applications, we might use techniques like active learning, where we try to have some labelers and humans in the loop, and these labelers look at the samples that the model is not confident on, and they try to provide the right labels for that. And then we collect such data and use them in addition to our training data for the next iteration of our training. Online learning is another technique where we expect our models to learn as the data changes. So there are techniques that you can just entrust your model and let it learn and adapt to the data as the data changes. So we have to make sure that we detect model degradation, and therefore model monitoring and versioning is important, because we should try to respond proactively, and also we might need to go back to different versions if our model has degraded. All right, so another point that we have to be mindful is automation. We try to automate any code that we need to run multiple times, and different codes need to be automated. As an example, the data preparation, the feature engineering code, and the extraction of the features from the data, and even training the model and evaluating the model, and also deployment of the model can be automated. And these are the parts that we need to run multiple times throughout the life of a machine learning project. So we try to invest in automating these codes, actually. So there are different levels of automation. The first level is to make sure that our code is modularized, and by that, we have to make sure that we have not hard-coded any parameter in the code that might need to be changed in the next iteration. The next level is to try to automate the training pipeline. So we just want to make sure that the training can be done smoothly. And the next level is to invest in CI/CD pipeline for machine learning. So I had to mention that there are reasons that we try to automate the code. The first reason is that we try to have consistency and make sure that human errors don't impact the processes that are iterative. And another reason is that when we automate our code, we can deploy and run and train our models quickly, and therefore we save time on the retraining of our models. So when it comes to CI/CD pipelines for machine learning, it starts from keeping the data in data store, and different versions of that data can be stored. Also, this is an automated pipeline. So after the data, it tries to run the code that extracts the features, and it keeps different versions of the features in a feature store. Then the code runs to train the model automatically and validate the model. And by validation, we try to make sure that our model works better than the previous models. And if you have some unit tests or some code that tries to handle the data in specific ways and deterministic, we can write unit tests and validate our code in that CI/CD pipeline. After that, there is deployment. So if our model is more accurate than previous models, we try to deploy that automatically. And also monitoring can be incorporated into CI/CD pipelines. Because this needs to be done quickly, containerization helps for specific reasons, because we can make sure that we have reproducible code, and containerization also helps with fast deployment of the code without propagating the changes to other components in the system. The last point to make is cross-functional team. So in order to productionize machine learning models, we need different disciplines. And in our machine learning project team, we have machine learning engineers who are in charge of implementing the models and making sure that the model is performant. We have data engineers who are in charge of data pipelining and orchestration of the data. Software developers focus on implementing features and integrating our machine learning project to the other components in the system. And DevOps engineers focus on the infrastructure and sometimes infrastructure as a code to make sure that we have the same infrastructure in different environments like test, staging, and production. User experience designers, we use them to make sure we have them in the team to make sure that we have seamless experience for the end users of our system. Business analysts and quality assessors and labelers also might be needed in machine learning projects. The point is that different team members are focusing on different aspects of the project. So we have to make sure that we have a collaborative team and they work together and interact with each other rather than having them in silos, which usually results in failure. And also this needs some leadership and sometimes structural change in organizations. So to summarize, we always try to upskill our clients to make sure we have reasonable expectations and vivid goals for our project. We also try to upskill ourselves and make sure that we are keeping track of up-to-date techniques and state-of-the-art models so that we can improve our machine learning models, and that is also important for productionization. We always start with proof of concept to make sure we reduce the risk and we make sure that our data is ready for a machine learning project. We try to invest in data pipelines as soon as possible so that we can do end-to-end testing of our machine learning model. And also this allows us to have more confidence that our model works in practice. We try to invest in machine learning pipelines and automating them so that we can retrain our model as quickly as possible without human intervention and error. And also, we try to use agile practices in machine learning projects, and therefore we try to prioritize in different iterations and sprints, and also we are in favor of iterating fast. And also having a highly collaborative cross-functional team is of extreme significance for machine learning projects. So this concludes the talk. Please feel free to contact me through my email or on LinkedIn. And also we have a DiUS Slack community that you can join and be in touch with us. And you can go to slido.com and ask any question that you have right now. I'm happy to take the questions.
Thanks very much, Shahin. My name's Alicia. I work at DiUS. Shahin, I'm just going to ask you some questions that have come through from Slido. Just a note to any other attendees, the link is there in the comment section, or you can join via that note on screen now. So Shahin, one of the questions that we've got that's come through is, do you have any advice on how to detect model drift automatically once an ML application is in production?
Sure. So this is where monitoring and logging is important. And we try to make sure that we compare the input and output of the model to the training data and the test data. And therefore, in logging and monitoring, we try to make sure that we keep statistics of the streaming data and compare that. And if it is very off compared to the training data, we should expect a drift. Also, out predictions, and we might see a slight and gradual change in those statistics. For instance, we can see that the model tries to predict more samples in a specific class compared to the test data, and that means that a model is taking place, and we can use logging and monitoring for the input and output of the model and try to have alerts that automatically inform us if the DS is if the drift is taking place.
Fantastic. Thank you very much, Shahin. Now, just having a look for some other questions just coming through. Another one that I have for you is, what are the special challenges for deploying a mobile ML application?
Right. So the problem with edge machine learning models is that we usually don't have on device are performant enough, but also their sizes are small. And sometimes, we've dealt with problems that we needed to download the model in real time on the edge, and we had to make sure that the model size is also small for such cases. Therefore, techniques like quantization help us with having models. Also, things like distillation and teacher-student learning allow us to have models that are smaller in size but are still performant, and we can use them in practice for edge detection. And because the model is smaller, we need less computation, and they can be used for edge devices as well. So just maybe it's good to mention that we worked on a phone insurance project that we needed to have an object detection model on the smartphones, and so we used techniques like quantization, and we had to make sure that the model is small enough so that it can be used in practice in real time, and it was processing the images coming from the camera of the phone, and it was processing them. So models that such specifications like mobile net models and similar approaches.
Lovely, thank you. Got one more question. Again, how does the ML team at DiUS make sure that the ML techniques being used are statistically correct?
Sorry, I'm repeat that question for me, sorry.
No worries, that's fine. How does the ML team at DiUS make sure that the ML techniques being used are statistically correct?
Sorry, what I'll do is that I go to the Slido to make sure I can look at the question at the same time, because I hope I am not dropping out. But 3, 2.
I'll pop it in the chat there for you, Shahin.
Yeah, that would be good as well. Thank you.
No worries.
Right. So being statistically correct. So it's a hard question to answer, and the way we try to tackle this problem is we try to have end-to-end systems after we make sure that our model is working accurately on the test and validation data. And that is exactly to tackle this problem, to make sure that our models are correct. And technically, there are other dimensions to this problem, and that is to make sure there is no bias in such data and the model itself. And there is no single recipe for that. We just have to try to spend time with the model and try to monitor the model itself and make sure we can try to find the statistical differences in our model and in the data in practice.
Wonderful, thank you very much. that is all our questions. As we said, you can jump into the DiUS Slack channel and to the AMA channel within our DiUS workspace and ask any questions of Shahin there. Before we close out, I was just going to hand over to Mark for some final comments at the end.
Yes, I was just going to say, Alicia, if you can still hear me, thank you everyone for joining us today. As Alicia said, we do have a Slack community workspace where you can join us and your peers. Ask any further questions there, we'd love to answer them. Just a reminder that this session has been recorded as well, so it'll be available on our DiUS YouTube channel, along with our other Lunch and Learns. And lastly, I just wanted to mention, and you may have already seen that we've recently launched a survey to understand the level of machine learning adoption. It'd be great, if you can participate with that. Your input would be fantastic. The aim of that is really to understand where organisations are on their journey, what application areas are they focused on, and what challenges are they facing. And great to see if they're consistent with the challenges that we talked about today, and whether some of those tips that Shahin has shared would be helpful there. So we do plan to share those results early in the new year. So if you haven't filled it in just yet, please do so. It's only a couple of minutes. Thanks again, and enjoy the rest of your day.